Okay, so welcome back, everyone. So today it's our pleasure to have Michael Muehlebach, who will be talking about learning in the presence of dynamics and decision dependence, and he'll be address robustness, adaptation, and serendipity. Yeah, thank you, Michael. Yeah.
Yeah, thank you, Mehdi. Thank you very much for the invitation, and it's a great pleasure and honor to be here. And so, yeah, I mean, I typically like to give presentations to a live audience. So if you want, you can turn on your camera. I think it's a bit more lively. And also, if you have questions, just jump in and interrupt, and I would be happy to answer it. And I need to admit that this is a very, very new talk. It's a very recent talk covering really recent work. And so I haven't practiced a lot. And so, so it might be a bit bumpy along the way, but let's see. Okay, so I'm leading the Learning and Dynamical Systems group at the Max Planck Institute. And in my interest and my team's interest is to develop machine learning algorithms for large-scale infrastructure systems and large-scale control systems. And by large-scale control systems, I mean, for example, supply chains, transportation systems, or industrial processes, right? And these are really large-scale, they're complex, they're interconnected. And so it's a challenge to develop learning algorithms for these systems. And the key questions I'm interested in is how can we get algorithms to be safe and reliable? How can we get them to be sample efficient and also adaptive? That's the last part, right? And when you think about these large-scale systems, an important aspect is that there's feedback loops everywhere, right? And this is going to be a central topic in today's talk, right? And usually when we make decisions, so when we say we set a price or and we provide a certain supply, for example, in a power grid, then the decision we take will influence the surrounding. It will influence the demand, influence the behavior of customers, and so on. And so there's an implicit feedback loop between the decision making and the environment. And whenever there's feedback loops, you have to be careful because sometimes there's just unexpected behavior that might occur. And I can illustrate this on the example of control theory. And so control theory has a really long history in dealing with feedback systems. I mean, control theory in a way is science of feedback, the science of feedback. And the example I would like to point out is an example from adaptive control. So specifically already in the 50s, people were trying to optimize the controllers of propulsion systems for aircraft, right? And the challenge there is that an aircraft might operate at various different operating positions. So say at sea level, at very high altitudes, at different speeds, so subsonic, supersonic, and you would like to have a control system that adapts, right, and that optimizes performance to all these operating conditions. And so a very simple strategy that one can imagine is to say, okay, let's collect data while the system is running and identify, say, the propulsion system, right? So the dynamics of the system as it operates. And if I have a good identified model, then I can use that to update my control design. And then I can iterate, right? But the challenge here is that when you collect the data, you're not observing the system in isolation, but you're observing the system at a certain operating point and it's operating with a certain feedback controller. And so you're observing the closed loop system. And so just to give you a simple example, a stylized example, so what you can see here is that, say the nominal system is the one in a dashed line, right? And you collect data, you identify the dynamics. So in this case, it would be an impulse response. And your model will predict the solid line, right? And at first sight, it might be that this is actually quite a good model, right? So it looks good, it's low order, and it does a reasonable job in approximating the impulse response. But then when you use this model to update the controller, the following might happen. So you might want to get a faster response, right? So you might want to improve your control performance. So you're pushing the boundaries, and using your model, you're predicting that you're going to get this very nice response, just going straight up to 1 extremely fast. But then what actually going to happen is you have this large oscillations, right? And the reason is simply that when you're making this prediction, you're actually predicting something for a new operating point, right? And the model that you identified doesn't necessarily generalize to this new operating point, right? And unfortunately, they sometimes can have drastic consequences. And here's one example where this research aircraft actually really died as a fault of this adaptive control mechanism. And why am I bringing up this example? Because I think it's, although this is research that started in the 50s, I think it's still very relevant today, where we're doing, for example, offline reinforcement learning, and where essentially this idea of doing iterative identification and updating control designs is very prevalent, right? But today my talk, okay, and so one of the conclusions is that whenever there's feedback mechanisms, you have to be careful, and there might be really unintended consequences compromising safety and reliability. And so in my talk today, what I want to highlight is I want to show you 3 different ways in which we can handle and deal with this situation. The first approach, I call this robustness, is simply to say that, okay, we should care about our decision-making strategy and care about the decision-making strategy, making the decision-making strategy robust. And I'm going to make this more precise. And if that is the case, then I can guarantee that even if there's feedback mechanisms, this is going to be working fine. Now, the second approach is going to be adaptation. So essentially algorithms that adapt to the changes in the data distributions, the changes that are induced by some of the environment dynamics. And the third approach I want to highlight is, and what I call here serendipity, is the fact that you can actually benefit from the feedback loop and use this decision dependence to your advantage. So you can not only react to the environment, but by your decision-making strategy and by the presence of this feedback, you can actively steer the distribution in the right way. And we're going to see that there's some interesting and cool real-world applications along the way, or at least connections to some real-world applications. So again, if you have any questions or comments, just raise your hand and ask. Okay, so let's get started. So the first part is this worst case point of view, right? And so we're dealing with this feedback mechanism where we have a decision-making strategy that influences somehow the surrounding and changes data distributions, as illustrated in this figure. And from a certain more abstract point of view, the way we can model this is simply as the interaction between 2 dynamical systems, in general S1 and S2, and their standard theory, for example, a small gain theorem that says that this interconnection is stable if the loop gain, so if the amplification over this first system S1 and the amplification over the second system, if this multiplied together is less than 1, then we can essentially guarantee that the closed loop system is also stable, provided that these S1 and S2 are stable themselves. Right? And what does this gain mean? Well, it just simply means you can think of this as an amplification from the input to the output. Right? So it's a very intuitive statement and a very intuitive result. And we can therefore use it for designing our decision-making strategy. In particular, what this theorem tells us is that, well, we should just make sure that this amplification from a change in the distribution to our change in decision-making is relatively small, right? Because this amplification characterizes the gain, and that's important, as pointed out in this previous theorem, right? And so the question we might ask ourselves is really, how do we ensure, for example, in the case of now machine learning and classification, how do we ensure that our decision boundary is robust to a certain shift in distribution, right? And this will then also guarantee stability if we have decision dependence. So if you have the presence of this feedback loop. And we did some work on this. So that's work by my PhD student, Melis, and it's work that I would like to highlight. So we looked at classification, and I think Boumediene might also like this because then there's going to be a connection to support vector machines. So in classification, the question is really, how is your decision boundary affected by changes of your data set, the changes of your training data? And there's two ways in which you can alter your training data. You can either perturb the features or perturb the labels. And while there's been a lot of work on feature perturbations, there's been less work on label perturbations. And so we looked at this scenario, right? And so the key question is, if you have a given classifier, how much, and I alter a few data points, a few labels in my training data set, how much is my decision boundary going to change, right? And from a security perspective, you can also think of this as an adversarial attack, or where there's an adversary that manipulates your training data, so to alter your decision boundary, right? And one wants to mitigate this effect. So one question that you might ask yourself is, well, given that we have all this data nowadays and we can effectively use the computes that we have, then maybe the models, as we have them and use more and more data, maybe the models are already robust enough, right, by themselves, simply because they've been trained on so many examples. And so Melis actually investigated this point, and she looked at a setup where we wanted to categorize movie reviews to be either positive or negative, as an example, right? And so here, for example, you would look at how susceptible the classification boundary or decision boundary will be to a few mislabeled reviews, right? And we looked at relatively large models, so transformer models. So we looked at Roberta as an example, and we found that test accuracy is actually quite impacted by this adversarial manipulation of the training data, right? So that's what you see on the right. You see how the test accuracy is actually decreasing when you adversarially perturb a few well-chosen data points in your training data. And now the question is, what can you do about this? So how can you reduce and mitigate this effect? And so in other words, how can you reduce this amplification over your decision-making strategy, right? And we decided to name our approach Floral, for flipping labels for adversarial learning. I think it sounds quite nice. And the idea is to use adversarial training and a variant of adversarial training. Now, adversarial training is based on minimizing or solving a min-max problem in the case where you have feature perturbations, right? So when you actually perturb the feature, then you can formulate this max problem, and you can try to solve this, right? But when you have label perturbations, it's a bit more complex because the labels is a discrete set, and this loss is usually a surrogate. So it's not exactly the misclassification or classification error that we really care about. At the end of the day, it's usually a surrogate. And so it's not so clear how you generalize this idea to the case where you have label poisoning or changes in the labels. And so what Melis did is she came up with the following solution. So the idea is to have this iterative process, and you can think of this as a game between a learner and the attacker or the adversary. And what the learner does is he suggests or she suggests a decision boundary, and then the attacker tries to finds the data points that influence the shape of the decision boundary most and then perturbs these, right? And then we just iterate on this. And it's nicely applicable to support vector machines, because when you have support vector machines, the dual variable directly, the support vectors directly tell you how influential is a given training data point, right? And so in the case of support vector machines, what you do is the learner propose a certain set of dual variables that gives rise to a decision boundary, and then the attacker will just take the most influential data points, so the top K support vectors, and then flip the label, right? And mathematically, if we write it down precisely, then we get this following bilevel problem. So the outer one is just the regular support vector machine problem where the Q matrix arises from the manipulated labels. And then there's the attacker here that just flips the labels of the top K support vectors, right? And so what's interesting is this algorithm is a dynamical system where you have this interaction between optimization and then label perturbation. And it works quite well. So we also combine this with neural network embeddings. So we use the same Roberta embeddings, but we put the strategy on top. And what you can see is that you can greatly improve test accuracy, even though you have perturbed labels in your training data set. So in effect, you reduce this gain by quite a lot that characterizes how susceptible your decision boundary is to changes in the labels of your training data, right? And well, Melis did also a lot of comparative studies with other approaches. A lot of the approaches are based on identifying labels that are corrupted and then sanitizing them. And it turns out that this floral approach is quite scalable and works quite well. And if you're also more interested into the details, I can recommend looking at our work. So we also analyzed really these dynamics, these training dynamics, and came up with stability results. And there's also some fun insights that you can look at when you try to understand which are the labels and which are the data points that are really influential. Yeah, so the details are in the paper. So with that closes the part on the robustness. I showed you one example with which you can get a classifier that's robust to changes in the training data set. And by the small gain theorem, by the small gain argument, it highlights that even when there's feedback loops, as long as these gains are small, it's going to be fine, right? And by our design, the classifier is going to have a low gain, and so it's likely going to be less problematic when deployed in the presence of feedback loops. Yeah. So let me know if you have questions, and otherwise I will continue. So the second topic I want to touch upon is adaptation, right? For now, we just adopted a worst case perspective. We just said, well, we're just looking at these worst case perturbations, but we can also adapt. And so I highlighted this by using this chameleon. Okay, and so what do I mean by the adaptation? One way to think about this is to say, okay, I'm also going to neglect this feedback loop, but I'm just going to look at distributions that change over time. And then the standard approach that also is being proposed in the community is to think about online learning and to formulate this as an online optimization problem. So, and the quantity of interest is typically regret. So what does regret do? You measure the performance of your decision-making, right? That's here. And this performance is going to depend on the different distributions, mu k, right, that influence your parameter. And you're comparing this decision-making performance to what you could have achieved had you known all the distributions ahead of time, right? So that's your benchmark. You're trying to get decisions that are robust to kind of an average or a sum of all of these terms, right? And what we did in this domain was to essentially see how the online learning algorithms, so a lot of this is based on online gradient descent, how this can be applied in the context of robotic systems. And in the context of robotic systems, there's usually constraints that arise. So constraints, for example, because you don't have a perfect model of the system, so you only have approximate gradients, or there may be other constraints induced by dynamics and so on and so forth. And so some work that we did was to understand essentially gradient descent strategies in this online setting, and to see what happens if we perturb the problem assumptions a little bit. And one particular and I think interesting result is that the standard approach is to say, okay, we have convex Lipschitz functions, we do gradient descent, and then we converge at the rate of 1 over square root of t. That's formulated here. But it turns out that even if you're in a scenario where constraints have to be discovered one by one, so where the decision maker doesn't have full access of the feasible set, but constraints are just flying in one by one, you can actually get the same convergence rate to the objective, and you can also guarantee feasibility in the long run by kind of a constraint optimization algorithm. So that's quite remarkable. So in this sense, the gradient descent algorithm is robust to the case where you also have unknown or partial information about constraints, or some constraints that are unknown. And then a lot of the work we also did was to look at what if we use finite differences for the gradients, or what if you use model-based and finite difference gradients and we combine these and so on, right? And but let me emphasize maybe the application in robotics and in really the control of dynamical systems. So here's a simulation example. So this is work done by Hao Ma, also one of my students, and he looked at this elongated beam, and this beam is quite high dimensional, so it's flexible. So it has about 150 states, if I remember correctly. And the goal is that you set a torque here, and with this torque, you excite the bending modes, and you want to have this tip to follow a given trajectory. And the 150 states, that's for reinforcement learning standards, this is really a lot. So a lot of the benchmarks I see there, I mean, they involve contacts, but they're usually on the order of maybe 20 degrees of freedom, so about 40 states, right? But here we have many more, and we can apply this online gradient descent or variants of online gradient descent. So in this case, we use a quasi-Newton method, and it works extremely well. So the goal here is to track different trajectories. So our learning algorithm sees different reference trajectories at every iteration, and these trajectories are just sampled from a certain distribution. And the goal is that over time, it can track all of these, right? And you can formulate this as an online optimization problem, the way I showed this. And we can also apply it for this Walker. That's a standard benchmark in reinforcement learning. But what we wanted here is we want to get a little bit of more fine-grained control. So instead of just walking forward as fast as possible, we're again thinking of reference tracking. So we want the end to follow these references. And in this setting, there's no gradients available, but what you can do is you can do stochastic finite differences. And it also works for robotic systems. So this is a robot we have in our basement, and this robot plays table tennis, and it's actuated by pneumatic artificial muscles. So it's quite fun. And this is the last example I can also highlight, which is also cool, a really cool system. The idea here is that we control the magnetic field inside this workspace. So we have 8 coils, and we control the magnetic field inside this workspace to move, to essentially move a small a catheter, right? A magnetic catheter, or a small robot that's also magnetic. And essentially these systems have applications in targeted drug delivery or minimal invasive surgery. But we're just thinking or using these systems to explore the boundaries of magnetic navigation or magnetic actuation. And in particular, one setup that we looked at is just to have an inverted pendulum here on the top. So the pendulum on the top is not actuated, and I can show in the video, but the pendulum on the bottom is actuated. So we have here the magnets, and we actuate the bottom part, and then we want to stabilize the upper part. And this is really a setup. It's an unstable system, so you really need feedback. So we have motion capture cameras and that record information, and then there's feedback control that stabilizes this pendulum. And the use of feedback in this context is really something new to this electromagnetic navigation community. And and I can come back to that. But first, with this online learning approach, what we can do is we can eliminate consistent steady state errors. So for example, if you do this tracking along a circle, what you can do is you can actually learn all the repeatable disturbances. And after convergence, you're essentially you still have the noise that influences influences your trajectory, but at least the repetitive disturbances can be eliminated, right? And this is the plot regarding feedback. So the interesting thing is that by using feedback with these systems, we can actually just control the torque. And the traditional way of operating is that you exert a magnetic field, and then you have the small robots to just align with the magnetic field. But if you do that, you need quite a lot of current. So that's the current you need here. And what we can do with just controlling the torque is we can reduce the amount of current we need to really below about 0.5 amps. And this is important because it means that we need much less cooling in these coils. And I mean, the system we're operating with is just a small scale example, but in the medical devices, these are much larger, and then cooling is really an issue. And so with this approach, you could simplify the design and reduce cooling. And yeah, maybe I'm going to skip this. I'm going out of time, I think. Anyway, so that's about adaptation. So yes, we can also adapt if distributions are changing over time, right? And I think in particular for many robotic systems, this has great potential. The algorithmic ideas that we use there are simply gradient descent type of ideas. And in robotics, the question is often, how do we extract gradients? And there, I think using models is usually a very good way. So using approximate models to get gradients and gradient information is usually very helpful. So now let's look at the last part, the serendipity part. And so here, the idea is really to exploit the fact that we have feedback, right? And so we can, because we have feedback, we can actively steer the distribution to our advantage. And let me give you a few examples of where this happens, right? So for example, if you're a political party that decides on how to align its ideology so that you get a majority of votes, right? Then you're thinking about, well, what's the interests of the people, and then you're aligning your ideology so that you reflect kind of the majority of the people, right? Or in the more engineering applications, if you're a grid operator that operates certain power plants, right? You have to think about the energy supply for the next day and the price at which you want to sell your energy, right? And so the demand that's in the grid will influence the supply and the price you're going to set, but vice versa, the price you're going to set will also influence the demand, because then people will economize. And similarly, the ideology of the party will then also influence what people are going to think, right? So there's this feedback loop. And if we want to take this feedback loop into into account, and if we want to take it to our advantage, which is going to be the main part of this the main message of this part, well, then we have to think about modeling the environment. So modeling how our decision actually influences the data distribution. And I'm going to show you two types of models, and we have results for both of these. The first type of model, and that's maybe more closely aligned with just reinforcement learning, is to say the environment just follows stochastic dynamics. So we have stochastic dynamics, so discrete time, and X is just finite dimensional, real valued finite dimensional. So there's continuous states and actions. But the trick is that we assume that we don't know. The decision maker ahead of time doesn't know how the environment dynamics going to evolve. So we have a set of M candidate models, and we only know that the environment evolves according to one of these candidate models, right? But ahead of time, we don't know which one of these F1 to Fm it is. So that's one model. So just modeling the environment is one of these stochastic processes, stochastic dynamical systems. The other approach is to say, okay, again, the environment evolves according to stochastic dynamics, but these dynamics are such that they're contractive. So it means that if I fix my U over time, my distribution or this random variables P are going to converge in distribution. So these are the two environment models that we're going to look at. And the question that I want to put up is, well, what are interesting or good decision-making strategies in these two type of environments? And can we say something about their sample complexity? So how many samples do we need to achieve a certain performance? Okay, so let's start with the multi-model perspective. And you can really think of this as online reinforcement learning. So the decision maker interacts with the environment and then tries to figure out the dynamics and make at the same time make good decisions. Right? And I think this is very relevant for many different applications. One application that I would be excited to look further into the future is the management of supply chains, where here, if you have a finite set of candidate models, you could use these models to, for example, incorporate different supply-demand prediction models, or also different lead times. So lead times describe the delays you have along your supply chain. And I think the fact that you have finitely many is actually a good way to incorporate prior knowledge and possible scenarios. Right? So from a certain point of view, it might sound a bit restrictive, but I think it's also a good way of baking in prior knowledge. Okay, so let's see. So here's the algorithm that we're going to analyze. And the algorithm is based on a very simple principle, and it's also, of course, connected to Thompson sampling and other approaches, but let me explain how it works. So the idea is that for each of the potential environment dynamics, F1 to Fm, you can compute a feedback law. So this feedback law, mu1, or policy in reinforcement learning, this mu1 would assume that F1 are the environment dynamics, and then mu_m would assume that Fm are the environment dynamics. Right? And this can be computed offline. And of course, from a computational perspective, this can be intractable, but because you have to solve really complex dynamic programming problems. But this is not something I want to account for in the analysis, right? I'm interested in the complexity of the online learning and the online decision making. So that's something that's not captured by the analysis, right? Okay, and then how does the algorithm then proceed? So we have this certainty equivalent policies. Then what we do online is we simply look at the posterior over models. We sample from kind of a modification of the posterior over models, and then apply certainty equivalent policies, right? And one of the tricks here is that we have to be careful that there's enough information in the system so enough excitation that we can distinguish two models. And that's exactly this part here where we wait for over m steps. So m is an integer, so that's just a constant, and this constant ensures that if we wait over m steps and we excite our system, then we can tell two models apart. That's what this m does. And then here we just proceed by looking at the one-step prediction error for the different models. And then this is essentially the posterior over the different models scaled by this parameter eta. And then we apply certainty equivalence plus some excitation. Right? And what's interesting is that we're not discretizing over states and actions, but we're discretizing over models. And I think this provides mathematically a very tractable framework for analysis. And in particular, we got this result. So we were able to understand and characterize policy regret. So really, how many samples do you need to achieve a certain regret? And so the result we got here is that if you have this persistence of excitation and you're careful about how much noise you inject to excite, you get a complexity that scales with log of the horizon, and particularly log of the number of candidate models, and then a dimension. So a constant that depends on the dimension of the states. Right? And this quantity here, this gamma, from a control perspective, this is the optimal H2 gain. So, but this from a reinforcement learning perspective, this is just the optimal performance you could get with a steady state feedback controller. Right? So this is the optimal steady state policy if you were to, if you had all the information ahead of time. Yeah. Okay. And so the punchline here is that because of this persistence of excitation, and I guess this assumption, and despite the fact that we have feedback structure and these dynamics, we can actually get a convergence rate here that's very reminiscent of the optimal rate that you can get in supervised learning. So essentially, under these assumptions, we get sample complexity results that are similar to supervised learning. Okay, and let me just emphasize a few more things. Here we operate under a finite class of models, so we get regret log n plus log m. But we can also extend this by applying covering and packing arguments. And then, of course, this m here will just be the packing number measuring the complexity of your function space. So more specifically, you say that you have a set of functions, and the set of functions is a bounded set in a normed vector space. And then the complexity of this function space or the set of functions is measured by the packing number. So it extends to a really broad class of functions. And if you have parametric functions, so if you parameterize your models, then the complexity, this log m, just boils down to be the p essentially, you'll then get policy regret that scales with square root and p, where p is the dimension of your parameters. And in principle, this applies to neural architectures such as neural networks and transformers and so on. Okay, so that's the first part. So the idea here is to do posterior sampling and to apply certainty equivalence, and we get some policy regret bounds. Now let's look at the other example, and here the assumptions will be that we have the environment dynamics are contractive, and so to be more specific, contraction means that if we fix the decision U and we evolve these dynamics, then essentially this random variable P will converge in distribution. And maybe more formally, it means that there's going to be a steady state distribution, and we can express the steady state distribution by essentially a steady state mapping pushed forward to this disturbance distribution. So one way we can characterize the steady state. And so the question is here, well, we have these interactions, and now, first of all, what is actually the performance metric we're after? And so we decided to look at the following performance metric. So here, the cost is this phi, and we said, okay, our performance metric is just, we want to essentially guarantee low cost, but when P is sampled according to the steady state. Right? So we measure our decision in terms of the steady state performance. And I should say this is work by Jiu He, and I think Jiu is even in the audience today. So it's great to have him. And here's the algorithm we looked at. So it's a variant of gradient descent, and it has a very clear interpretation. So the important aspect to consider here is that there's going to be two terms. One term is the adaptation. So that's also the second part of my talk that discuss this. But here's another term. It's the anticipation and the steering term, right? So because there's this feedback loop, there's going to be a connection between our decisions to the changes in the data distribution. And this is essentially measured here by the steady state map and by this term, right? So here with this variant of gradient descent, we're really accounting for the fact that there's this feedback loop and there's this decision dependence. And you worked out convergence guarantees. And here's just the most basic version of these. So we looked at here the squared gradient norm according to this performance metric I mentioned earlier. And this applies to non-convex functions as well. And you also worked out high probability bounds that are a bit stronger than what we have here. But an interesting observation is that, again, here, even though we have this dynamics and this decision dependence, provided that we're smart about evaluating our gradients, we can actually get optimal convergence rates. So we get the same convergence rates as SGD, despite the fact that we have all these dynamics and this additional complicating structure. Right? And let me maybe just illustrate this point on an example. So the first example is a stylized model of a recommender system. So say you're a movie platform that gives recommendations about what movies people want to watch. And so P is essentially the recommendation or the choices or the preferences of the different users, right? And the preference at time k+1 is going to be in this model going to be affected by the preference at time k, the prices that we set, right? And then some initial preference that you had initially, right? And of course, there might be also disturbance and so on, but it's very stylized. So we took the disturbance effect away here. And what's our objective? Here, the objective from the movie platform will be to maximize revenue. So we have this in the product, but then we might want to care also about diversity. So we want to have maybe a diverse choice distribution so we can emphasize this and put this into our objective by regularizing with an entropy term. And so this is a non-convex problem. But what's the important point I would like to make, if you just naively do gradient descent, then you're following the blue curve, right? And so it means you get stuck, right? Because you're not accounting for the fact that there's this interaction between the price you set and the preferences of the users, right? And but if you model this term and if you account for this, then you're on the red line and you're really converging to an optimal steady state behavior, right? That's the insight here. And this actually also applies in engineering systems. So this is a more realistic simulation of a power distribution network. So it's according to an IEEE standardized bus setup. And the goal here, or the challenge here, is that you want to regulate the power on this network, but there's suddenly 15 photovoltaic generators that are being added. And in each of these generators, what you can control is the amount of reactive and active powers that you inject, right? And so in a way, what you want to, the key quantities are essentially the voltage in the grid. And so you want to keep the voltage in a certain threshold, in a certain operating band. But at the same time, you want to really benefit from these photovoltaic generators. So you want to maximize active power and then not consume too much reactive power, right? And these are the results of the simulation. I mean, it's a standardized simulation. but these are the results with the current approaches, which essentially are based on lookup tables, are static feedback laws that kind of connect voltage drop to reactive power. And if we apply our strategy, this online gradient descent strategy instead, we can get a much better performance. So we can control the voltage quite precisely, and more importantly, reduce the amount of reactive power. So we're really benefiting from these additional photovoltaic generators from the energy provided by the sun. Okay, and so that concludes the 3 parts I wanted to highlight. We saw the first approach where we wanted to ensure robustness of our decision making and decision boundaries, so that if we have robustness, we can at least be sure that if there's a feedback loop, but if the interactions and the environment dynamics are relatively benign, then we can still guarantee stability even if there's closed loop. We looked at adaptation, and we looked at how this can be used in robotics. And then in the last part, we looked at 2 strategies that you can apply when you actually want to take advantage of the fact that there's this interaction. And with that, I would like to thank the people in my team, and I would like to thank you for your questions. Yeah.
Yeah, thank you very much. Thank you.
Let me know. Yeah.
What is it?
Let me know if there's some questions, or if
Yes, exactly. Yeah.
Clear, or yeah.
Are there any questions or comments? Yeah, we can't hear you. There's a problem with your audio.
Oh,
Yeah, maybe,
too bad.
yeah, maybe you can write it on in the chat.
I hope. Yeah.
Yeah, I mean, yeah, I think there's a, yeah, I think he wanted to ask a question.
I'm also not sure if I can actually see the chat, because
Yeah, but I'm just
you
waiting for
can
him to write the
can
question.
read.
I'll let you know if there's a question in the chat.
But,
Yeah, don't worry. I'm just waiting.
yeah. Yeah, I mean, we can also keep it short and
Okay, yeah, exactly. So yeah,
enjoy the rest, enjoy the
yeah,
rest of the day.
yeah. So he wrote the question: how does your work relate to similar work in online data assimilation?
In online data assimilation. So I don't know exactly what you mean with online data assimilation, but of course there's a lot of related work on all of the topics I touched, right? And so yeah, I think so. In the particular example, in the first example, right, on adversarial training with the label poisoning, a lot of the strategies that have been used are kind of like outlier detection. So you'd have a 2-stage approach where you'd first figure out, well, what are the outliers, and then you try to correct your training data, to sanitize your training data to do that. And I think what's nice about the Melis approach is that it's quite scalable. So while these 2-step approaches might work in low dimensions, it's not so easy how you do this in higher dimensions. And the approach that Melis proposes is also kind of just a single approach where you just update the training routine. Right? Then in the online learning part, of course, there's also a lot. This is such a rich topic, and I think the sort of relations is that we really, one part of the work was really to think about constraints. So what if constraints are not known ahead of time, but they come in one by one? And another part of the work was to think about how to compute gradients in the case of robotic systems. yeah. So that's, and in the last part, there's quite some recent work that also, I mean, this sort of feedback mechanism and decision dependence is also kind of an emergent topic in machine learning. And a lot of the work there has essentially used quasi-static models. So essentially that they're simply a map from decisions to distribution and so on, right? And what I think the two ways, or what's interesting in the work I showed, is that there's really environmental dynamics. So these the two environment models are really dynamic. So there's dynamic stochastic processes, and you have this interaction between the learning and the continuously evolving dynamic environment. Right? That's the two things. Yeah.
All right. Any other questions? Yeah, okay, seems not. Yeah, thank you very much, Michael, and
Yeah.
thanks everyone for coming, and maybe I'll see you in Japan.
Yeah, it would be nice. Yeah.
Yeah,
Yeah.
all right.
Yeah.
Okay,
Good.
take
Ciao.
care.
Have a good
Thanks,
evening.
bye, bye, bye.
Yeah.